Welcome back to this module on exploiting TLP to improve Unicore throughput. The topic of this lesson is simultaneous multithreading, which is a form of hardware multithreading in which the core fetches, issues and executes instructions from different threads simultaneously. Let's first motivate simultaneous multithreading, SMT. First, coarse-grained multithreading, block multithreading, does not perform well on out-of-order superscalar cores because there is a high cost of switching thread. The number of instructions in flight in a multiple issue processor is very large, meaning if we switch to another thread and we flush all the instructions currently in the pipeline, the cost of switching threads will be too high. Furthermore, fine-grained multithreading, interleaved multithreading, also doesn't match with the peculiarities of out-of-order superscalar cores because instructions can stay in different pipeline stages for several cycles. Remember Tomasulo algorithm? Issue, execute, write result, commit. Each of them are stages and may be comprised of several cycles. Simultaneous multithreading takes hardware multithreading one step further by fetching, issuing and executing instructions from different threads each cycle. So if this figure on the left-hand side illustrates execution on a superscalar processor where we have all the empty issue slots, this illustrates coarse-grained multithreading, block multithreading, where there is a little bit of cost, and this cost is too high in out-of-order cores, but here I assume a cost of only one cycle to switch to the green thread. It fills some of the vertical stall cycles, but it doesn't get rid of the horizontal wasted cycles. Interleaved multithreading looks like this. Again, it tries to reduce the vertical stall cycles, the vertical waste. It doesn't get rid of the horizontal waste. Simultaneous multithreading, which is illustrated here, means we issue from a different thread, from several threads each cycle. For example, in cycle 1 we issue 3 instructions from thread 1 and 1 instruction from the red thread, thread 2. And in the next cycle we issue 2 instructions from the red thread and 1 instruction from the blue thread, and we still have 1 waste slot. So the goal is to make better use of the available ILP hardware by executing and issuing several threads at the same time in a simultaneously multi-threaded fashion. Before I delve into the details, let's have a top-level view at the hardware requirements of simultaneous multithreading. Of course, the architectural state, meaning the architectural register files, the program counters, etc., they need to be replicated. Anything that is needed to save a thread, to save a process in operating system terms, needs to be replicated. On the other hand, the physical register file, the renaming registers, they can be shared because we have several threads at the same time and each can be allowed to use some of the renaming registers. SMT also typically requires replicating the fetch queue, one fetch queue for each hardware context thread, the reorder buffer, one reorder buffer for each thread, and the load store queues for each thread. Furthermore, the data forwarding must be thread aware. If a result is written to the common data bus, like here, the reservation stations need to know, does the currently finishing instruction belong to the same thread as the thread I belong to or not? Only if it writes a reorder buffer entry that of the same thread, then I can potentially be dependent on it. So every in-flight instruction basically must carry its thread identifier, its thread number. Also flushing must be thread aware, because we need to match the thread idea of every in-flight instruction with the thread idea of the instruction causing the flush, because only instructions that belong to that thread causing the flush need to be flushed. Also, instruction scheduling must somehow be thread aware, because when the result is communicated, is broadcast on the common data bus, only instructions in reservation stations with the matching thread idea can be issued. Similarly, or not similarly, but also the instruction cache needs to be multi-ported to be able to fetch an instruction from different threads each cycle. But is this a change to the organization of superscalar processors? The answer is no, because in a multiple issue processor, in a wide issue superscalar, the iCache also needs to be multi-ported, because we need to be able to fetch from different cache blocks in one cycle. SMT, simultaneous multithreading, also makes the design of hardware of superscalar cores simpler. Let's look at an example. If we have an 8-issue superscalar and we execute only one thread on them, then basically we also need to make sure that the front end, the instruction fetch unit, is able to fetch 8 consecutive instructions in the dynamic execution order every cycle. Unfortunately, these instructions are not necessarily consecutive in the program code because of the malicious branches. And fetching 8 consecutive instructions is highly complex. For example, suppose that our current program counter points to this instruction here, and the four boxes here denote one cache line. If this is a branch and this branch is taken or predicted taken, then the next instruction in the dynamic execution order is this one, then this one, and then again we have a branch, and the next instruction in the dynamic execution order are these ones, these 3 green boxes here. In fact, it's much easier to fetch 2 instructions from 4 threads each cycle, because we can fetch 2 consecutive instructions if they are in the same cache block, and we use multiple cache banks to support parallel access. In fact, this is much easier to implement. Even though modern processors don't do this, they fetch from a single thread, but they issue from several threads at the same time. Another example of how simultaneous multithreading reduces somehow the complexity of superscalar ILP hardware. In a single-threaded 8-way superscalar, we need to be able to rename 8 instructions each cycle. Or we need to split it, which increases the branch penalty, etc., etc. Everything is a trade-off. And to be able to rename these 8 instructions, this is highly complex due to dependencies, because the dependent instructions need to change their physical source registers. In fact, we may need to rename the same register several times in the same cycle. And such conflicts are simply less likely to occur when we have a 2-way out-of-order multiple issue superscalar processor, with 4-way simultaneous multithreading.
This completes this lesson. Thank you for watching. In the next lesson, I will give some examples of processes that support simultaneous multithreading. Stay tuned.